Finding the right chunk is not the same as ranking the right document. MaxP, SumP, and FirstP decide how chunk scores become document rankings. You'll understand the pattern behind a pipeline that weighs MaxP, SumP, and FirstP scores to surface the strongest document response. I'm Professor Pi, teaching search and IR with simple Python. Long documents are messy. A user asks a question, and the answer might live in one sentence or spread across many paragraphs. Engineers split documents into chunks and score each chunk against the query. The hard part is turning those chunk scores back into a single document score you can sort and present. At the core, this is about how you treat evidence. Do you trust the single best passage? Do you add up everything that looks okay? Or do you bias toward the start of the page where summaries often live? Each choice changes which document wins and why. Here is the simple idea. Imagine 3 documents, one with a single shining paragraph, one with a couple of steady paragraphs, and one with something helpful right at the top. MaxP picks the shining paragraph. SumP rewards steady support. FirstP trusts the opener. That gives you a mental model to predict which document will win before you run anything. We will build a tiny example that scores a handful of chunks, then roll those into 3 aggregators, and finally compare their ranked outputs on a simple metric. You will see why a spike can mislead and how a tuned rescue can recover buried evidence. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now let's surface the chunk level view so we can see exactly what each aggregation has to reconcile. This snippet surfaces the best chunk per query, so you see what passage level evidence MaxP, SumP, and FirstP must reconcile. Chunk level ranking is where many neural re-rankers leak relevance, because we often drop the most useful chunk when the document aggregator bottoms out. The tiny dictionary in chunk scores simulates 3 long documents with uneven gains distributed across their span. By flattening those scores into chunk rank, we can inspect whether the strongest signal sits early, midway, or deep inside the document. That visibility is crucial when diagnosing why evidence-rich documents like DocC might be demoted later. The output highlights the highest scoring chunk, reminding us exactly which passage drives every downstream decision. Seeing the chunks shows the risks of a one-shot decision. Next, we collapse chunks to documents by trusting the single best passage. This example applies max scores via MaxP so you can see how a single peaked chunk elevates a document above its peers. MaxP is beloved for cross-encoder re-rankers because it trusts the best passage blindly. But that strength becomes a liability when relevance is spread out. Here, max scores collapses chunk scores by taking the maximum per document, creating rank MaxP that mirrors many production re-rankers. Notably, DocC jumps ahead because it owns the only chunk scoring 0.74, even though DocB carries 2 strong passages. A seasoned IR researcher will immediately worry about robustness if that spike came from hallucinated context or annotation noise. The printed MaxP top doc confirms the winner under MaxP and quantifies its margin, priming us for richer aggregators. MaxP can ignore steady evidence. So now, we switch to adding up support across a document to favor consistent signals. This code extends the aggregation pipeline with some scores so you can judge whether dispersed evidence is rewarded. SumP often outperforms MaxP on long documents because it rewards consistent support across passages. Yet, it can overfit to noisy expansions. The comprehension that builds sum scores keeps the same chunk scores input, but accumulates every chunk score before ranking. Rank SumP reveals doc B contesting doc C because two solid chunks sum higher, while doc A fades despite its leading head chunk. Margin SumP quantifies how decisively SumP separates the first two documents, giving you a feel for headroom before switching aggregators. The printed SumP top doc shows the SumP winner and the margin over second place, highlighting how broader evidence tips the scale. SumP helps when many small clues matter, but web pages often front-load summaries, so a heuristic that prizes the opening chunk can be useful. We will test a softened FirstP that can be rescued by strong tails. This snippet stress tests FirstP by combining first vals with res vals, so you can see how tail evidence rescues a document. Pure FirstP trusts the opening chunk, which is convenient for web snippets, but hazardous once relevance hides deeper in the document. FirstP Rescue checks gap value between head and best tail chunk, adding burst weight scaled credit only when the tail is convincingly higher. Iterating over chunk scores fills first vals and res vals, so you can directly measure how much probability mass you recover by peeking deeper. Raising burst weight increases the boost, while shrinking gap clamps the rescue closer to vanilla FirstP, so you can tune caution. The printed Rescue Top Doc reports the rescued winner and the lift over pure FirstP, making the adjustment's impact obvious. Now that we have 3 scored orders, we need a simple way to compare them numerically, so we can choose the most reliable aggregator. This code scores each aggregator with a quick DCG-based nDCG, so you can pick the most reliable long document ranker. We pre-compute disk as the familiar logarithmic discounts for the top 3 ranks, and derive ideal docs from QRELs to get the oracle gain. The loop compares rank MaxP, rank SumP, and the FirstP variants by folding their orders into one weight vector, keeping the math transparent. Because we update best in place, you immediately see which aggregation style maintains graded relevance rather than trusting an anecdote. If you expand to more documents, extend disk with additional discounts, so the normalization stays correct. The printed best nDCG tells you which aggregator wins on this query and reports its normalized gain, anchoring the earlier qualitative comparisons. In a real system, you would run this over many held-out queries. The toy output points to patterns, not final answers, and helps you pick which aggregator to tune next. What this is: 3 ways to turn chunk evidence into document scores. When to use each: pick MaxP for short authoritative passages, SumP for long documents with spread support, and FirstP for web pages or summaries. One short warning: a single high chunk can be noise, and blind MaxP will amplify that error. Try a focused next step. Tune the burst weight and gap threshold on a held-out set such as MS Marco to see how much rescue helps in your domain. If practical IR tutorials help you, subscribe and watch the IR videos.